Now let's look at question number 2 on entropy. The question states a fluid undergoes a reversible adiabatic compression from zero point 0.5 megapascals, 0.2 meter cube to 0.05 meter cube according to the law PV to the power 1.3 is equal to constant. Find out the change in enthalpy, internal energy and entropy, and the heat transfer and work transfer during the process. Now, this is the diagram to consult, which is a PV plot, and this is compression. So, this is state 1. The volume is 0.2 meter cube, and the pressure is how much? 0.5 megapascals. And so this is V1. V2 is how much? 0.05 meter cube. So there is a reduction in the volume, so it indicates compression. And this is P1. P2 is something we don't know, so let's put a question mark in front of P2. Now this is a question in which we have to find out the delta H, the delta U, okay, and the ds. Dh you have to find out, du, and we have to find out ds, okay, and then we need to find out dq and then dw. Now if you look at this is a system which is closed, okay, and for a closed system, if you apply the combination of first and second law, you would get this relation: TdS is equal to dH minus VdP, if you remember the 6 equations that we discussed. Okay, and this is a reversible adiabatic process which is undergoing in a closed system. So because it's a reversible adiabatic process, if you remember the concepts in the entropy generation in closed and open systems, if it is a reversible adiabatic process, it has to be an isentropic process as well. So ds becomes 0. So this would give us dH is equal to VdP. Okay, so let's write down some data which is given to us. So P1 is 0.5 MPa, and V1 is 0.2 meter cube. P2 is nothing, we don't know about the value, and V2 is 0.05 meter cube. Now we have to find out the value of P2, and if you go by the law which is governing the process, you would get P2 by P1 is equal to V1 by V2, because that is inversely proportional to the power n, and the value of n over here is 1.3. okay, so P2 would become 0.5 into 0.2 upon 0.05 to the power 1.3. so take out your scientific calculus. This value would be how much? Around 3.03 megapascals. So this is almost 3 megapascals. So you can see a significant increase in the pressure by decreasing the volume. Okay, so let's bring this equation to the forefront, and let's say dH is equal to VdP. Now why we are using this? Because we have to find out the change in enthalpy. Okay, so let's find out, let's use this equation now. So this is the change in enthalpy, so it would be equal to integral H1 minus up till H2, which is dH is equal to integral P1 to P2 VdP. Now the integration is with respect to P, so we need to replace V with something. Okay, so if you look at the relation or the law, which is PV to the power 1.3 is equal to P1 V1 to the power 1.3. So from here I can say the value of V, if I find out, it would be equal to P1 V1 to the power 1.3 divided by P raised to the power 1 by 1.3. Okay, so let's put this value of V over here, and this would become H2 minus H1 equal to integral P1 to P2 P1 V1 1.3 upon P to the power 1 upon 1.3 and then dP. Now P1 V1 is basically a constant value. Okay, so when you solve it, it will give you, when you solve this integral, okay, this will give you 1.3 into P1 V1 minus, or you can say P2 V2 minus P1 V1 upon 1.3 minus 1. Okay, and you can put in the values over here. So the value would become H2 minus H1 is equal to 1.3 upon 0.3. Okay, now P2 is how much? 3.03 megapascals. Now this is megapascals. Okay, we need kPa, that is kilopascal. So we'll multiply this by 1000. So we will get 3030 minus, into V2. V2 is how much? 0.05. Okay, minus P1. P1 is 0.5 MPa. So it becomes 500 kPa. So this becomes 500. Alright. And into V1, which is 0.2. So when you solve this, the delta H comes out to be 223.3 kilojoules. So this is the change in enthalpy during the process, which is 223.3 kilojoules. Now the next part is to find out the change in internal energy. Alright. We all know that H is equal to U plus PV, isn't it? So we can do a very simple calculation over here. We know that H2 minus H1 is a value which is known to us. So we can write down VU2 plus P2 V2 minus U1 plus P1 V1. So you put in all the values and find out the value for U2 minus U1. And that would be H2 minus H1, alright, plus P1 V1 minus P2 V2. So this would be the value for change in internal energy, and you put in the values over here, and this would come about to be around 172 kilojoules. So this is the change in internal energy, and this is how we find it. Very, very simple. Okay. The next part that we need to find out and calculate in this question is the change in entropy. Now because this is a reversible adiabatic, so this becomes an isentropic process, so the change in entropy will be 0. So there is no entropy change, the entropy stays the same. Then it asks us the heat transfer. Now it is given to us, it is an adiabatic process. Adiabatic process means Q is equal to 0. So there is no heat transfer as well. So this is again 0 in going from 1 to 2. The last part is to find the work transfer. Now the work transfer is something we can always calculate. Okay, so work in going from 1 to 2. And we can apply the first law, which is Q1 to 2. Okay. Minus U2 minus U1, which is the change in internal energy. Okay, and this would be 0 minus 172 kilojoules. This will be minus 172 kilojoules. Now because it is a compression process, it is bound to be a negative work, because you have to provide some work to the system to compress it. So it is negative work. So it is a justified value. Okay, so The question is pretty simple. So you have to combine the first and second law. And how do we come to know we have to combine? Because it is asking you to find out enthalpy, dH, du and ds. So it is now clear that it will use a combination of first and second law, and because we have a closed system and that is too reversible and adiabatic, so this is the equation to use. And because it is reversible in and adiabatic and it's a closed system, it would be a it would be an isentropic process. So rest is very simple calculation which is very basic in nature, and it uses the basic concepts that we have studied in the video. So this completes the topic of entropy, and after this let's move on to the next set of topics that talks about available energy, availability and irreversibility.